Let's do some rotational kinetic energy problems. So this was one of my favorite problems. We've got a ball sitting at the top of a hill. We're going to let it roll down the hill without slipping. So it actually rolls. It doesn't just slide down the hill. And we're going to do two different versions of it. One where this is a solid ball and one where this is a hollow ball where all the mass is out at the edge. So let's do the hollow ball first. So a hollow sphere of mass m. We're going to use conservation of energy. So I'm doing this problem first, and then I'll come back up and do this one. So our ball is hollow. It's going to roll down the hill. We want conservation of energy. The potential energy it starts with will be converted into translational kinetic energy. That's the center of the mass of the ball moving down the hill, plus rotational kinetic energy. That's the ball moving, spinning, rotating. So potential energy is mgh. Translational kinetic energy of the center of mass is 1/2 mv squared, and rotational kinetic energy is 1/2 I omega squared. Remember, in rotational, everything in rotational, the version of mass is I. That's a measure of how hard it is to make something rotate. And the version of velocity is omega. So these two formulas are really the same. That's just the rotational version of mass and the rotational version of velocity or speed. Now we can simplify all this. If we recall, this is the key to all of these problems. V equals r omega. V is the speed of the center of mass, but that's also the speed of a point on the edge. So if we imagine putting a piece of tape here on the ball and watching how fast that piece of tape moves as we rotate down the hill, that's the same speed that the center of mass is moving down the hill. So that's the key to this kind of problem. V equals r omega. So we can plug then omega equals V over R into here, and then our equation only has V's in it. And the moment of inertia of a hollow sphere, we looked this up in a table, is 2/3 mr squared. So we substitute that in for I, we substitute this in for omega, and we get this equation. Just doing some simplifying and adding our fractions together, 1/2 plus 1/3 is 5/6. The m's cancel, this is independent of mass, and we get V equals 6/5 GH all under a square root. That's how fast the center of mass is moving when we reach the bottom. If we wanted to find out how fast we were rotating, we would take this, substitute it right here in for V, so that value divided by R is how fast we're rotating, our angular speed in radians per second. Now let's do the same problem, but with a solid sphere, where the only difference is we have a different moment of inertia. The moment of inertia for a solid sphere is smaller than it is for a hollow sphere, because in a solid sphere, the mass is more uniform. A lot of mass is closer to the center. The further away mass is from the axis of rotation, the harder it is to rotate. So this guy, the solid sphere, rotates easier than the hollow sphere, which means he'll rotate faster. His final velocity is going to be bigger. So it's the same idea. We're just using conservation of energy, potential, plus kinetic, translational, plus kinetic, rotational. Using all the same substitutions, we get this final value for the final velocity at the bottom of the hill. Notice L plays no role here. Everything depends on H. Mass plays no role. This was literally the problem that Galileo did to realize that everything falls at the same rate. Galileo didn't actually drop masses from different heights, he rolled different masses down a hill and realized that as long as they were the same kind of object, he had two different solid balls of two different masses, everybody reached the ground at the same time. Okay, another problem. This one, we could do a very, very hard way. We could use torques and free body diagrams. We could make this a very complicated problem, or we could use conservation of energy and make this an easy problem. So we've got this mass hanging on a string, and that string is wrapped around this disc that's attached to something here at the center. So as this mass drops, it's going to make this disc rotate. We're told a bunch of information, how far the mass drops, how long it drops. We're going to figure out what the mass of this disc must be to satisfy all these conditions. So we're just going to use conservation of energy. The change in potential energy of this mass dropping, mgh, mg change in h, all that energy will be converted into the translational kinetic energy of this mass dropping, plus the rotational kinetic energy of this disk spinning around. So we need first to find our final velocity of the mass dropping. So we just use kinematics to do that. We're told our time, we're told our change in height. We can find our acceleration. From that, using Vf as V naught plus At, we can find our final velocity. It's a negative velocity because the mass is dropping. Now we just use conservation of energy. Mgh will all get converted into translational speed of the mass dropping plus the rotational kinetic energy, translational kinetic energy, plus rotational kinetic energy of the disk spinning around. Just like the problem before, this is what we're always going to use in these problems. We're going to use V equals R omega. The speed at which this thing is moving is the same speed at which a point on the rim is moving, because these are attached by this string. So this block is dropping. If we were to put a little piece of tape here and watch that tape move around, that piece of tape is going to be moving with the same linear speed as this mass is dropping. That's the key to this problem. V equals R omega. And that V represents both the speed that this mass is dropping and the speed of a point on the rim. So we just plug in V equals R omega, which means omega is V over R. Plug in our moment of inertia for a disk, 1/2 mr squared. We look that up in a table. Plug in all of our values. We just found V. It's -3. That's not going to matter because we squared it. That'll just be 3. And we solve and get mass is 46.5 kilograms.